review, today we're going to go over and discuss reading the layers. Now, on your paper that you have in front of you today, it looks like this, but you have some information at the top, and it tells you that stratigraphy is a branch of geology which studies Earth's history as revealed in sedimentary rock. Have we been studying Earth's history within the rock layers? Yes, okay, so that's stratigraphy. Sedimentary rock is a type of rock that is formed by sedimentation. What does sediment mean? What does it mean for things to sediment, for a sediment, like settle? It's the settling of stuff. And that settling of stuff creates layers of rock, okay? Excuse me, it's called deposition. All right, so sedimentation of materials at the Earth's surface and within bodies of water and makes up about 3/4 of the Earth's surface. Now, here you're going to study the diagram to interpret the geologic history, and you're going to use these, what did I call them on here, principles to explain why. So basically, these are not necessarily principles, but these are explanations of why you chose your answer. We already know that our major principle is the law of superposition, which states that what rocks lie above? Younger rocks lie above older rocks. So that's what your basic principle that you're going to use to be able to layer this rock layer. However, you have to have a backup plan on explaining why you chose that information, which are these four things here. You're either going to say the oldest rock is on the bottom if the layers are not disturbed, which essentially is the law of superposition. You're either going to use an intrusion is younger than the rock layers it cuts through, which we understand that features and events are younger or older? Younger. A fault is younger than the layers that it breaks. Again, that's the features and events are younger. Or don't forget about the unconformities. Is an area where erosion has been removed from some layers. Let's talk about that just for a second for review. An unconformity is where there's no rock layers there. Now remember, scientists study different rock layers from different parts of the world. So therefore, they may have one rock layer from, I don't know, let's see, eastern part of the world, and one rock layer from the southern part of the world. They start to match them. Remember, we started matching them side by side. Remember? Kennedy came up first and started helping us put them together. And let's say the bottom, the lowest level of the rock layers, they match. And they move up and they see that that matches. And they move up and they see that that layer matches. They move up, they see that that layer doesn't match. They don't stop there because there may be other layers. And they say, okay, well, that layer doesn't match, but all of the subsequent layers above matches. So they can conclude that these rock layers are correct, but from an eastern part of the world where a rock layer doesn't match the southern part of the world, they can say an unconformity has occurred whereby the rock layer is missing. Two ways. What were the two ways that a rock layer could be missing? Or two reasons why a rock layer could be missing. Again, that's gaps in history. Erosion. What's erosion? Water and wind uplifts it and moves it away. So they could conclude that in that part of the world, what may have happened? Not erosion, but how does water and wind move it? What are some things? Tornadoes, floods, hurricanes, anything like that could have possibly occurred in that part of the world during that time to wipe away that entire layer of rock. Or another thing could have been non-deposition, where the rock layer was not put there at all because there was nothing going on, and that would be an explanation of ice age. Got it? Okay, so let's now move on to this. Let's take a look at this layer, these layers of rocks here, and you should be able to see all of the letters going on here. Now, number one said the oldest fossils would be found in rocks labeled F, E, J, or D. You have to choose which one. So remember, within your rock layers, how we identify the age of the rock and how we actually study it, keep in mind you don't go to the part of the world and look at the ground and say, touch it, taste it, throw it in the air and see if it flies west, east, south, or north, and say, yep, this layer has changed over time. How do they determine that the layer has changed over time? They have to dig it up, and they study past life, and those people that do that are called paleontologists. And in those past lives, with the past life, what are the things that they dig up? Fossils. Okay, so fossils are within the rock layers. If a fossil is in the lowest layer, that fossil is said to be older or younger than a fossil in the highest layer. Older. Okay, good. So the oldest fossils will be found in rock layers labeled F, E, J, or D. Which one? You're saying E as opposed to F, J, or D. Okay? Anybody disagree? What did you use these three reasons to explain yourself? These four reasons up here at the top. Which one would you say would be an explanation of your choice? A reason for your choice? I, which is the oldest rock layers at the bottom. Is that a good explanation of why you chose E? Everyone understand how we're doing this? Okay, very good. Are you all with me? Excellent. All right. The youngest rock layer, is it labeled K, E, F, excuse me, K, E, A, or F? F. Does anyone disagree? Okay, what would be the reason for explaining your answer out of the four choices? Are we talking anything about an intrusion? Nope, this is not dealing with anything with an intrusion. I. It's called deductive reasoning, meaning that it tells you that the oldest rock is at the bottom layer, therefore, where's the youngest rock? At the top. You can conclude that if the oldest is at the bottom, your conclusion can be the youngest is at the top. Again, that's deductive logic. Doing that helps you build on your brain cells and helps you be able to create that critical thinking that you guys just don't have yet, but I'm helping you to build that. So that was college thinking there. Alrighty. Which is older? Igneous intrusion, A. So it's talking about this, obviously, because it's an intrusion. Got it? Or fault H. You're saying A is older? Raise your hand. Raise your hand. You're saying H is older, meaning that it happened first or it happened later? It happened first, okay? Anyone disagree with that? Don't think I'm putting it down because it's right. I'm just putting it down because that's what you said. Everyone agrees with that? Okay, not looking at these reasons right now. I want to know your reason for telling me that H is older. Excellent, excellent, excellent. She says that the intrusion went through more layers, which means those layers had to exist for the intrusion to go through. H only broke, not broke through, E, G, L, and C, right? It didn't break M, D, J, and N because if M, D, J, and N were there, then it would have broken. But they must not have been there because they didn't get broken. Does that make sense? Yeah. Excellent. Very good. All right. So then what is, you have a question? Yes, H is correct. So now looking at those four reasons to back you up, which one would it be? 2. The intrusion is younger than the rock layer it cuts through. Or fault is younger than the layers that it breaks. Three. Triple I. Well, let's look at it. An intrusion is younger than the rock layers that it cuts through. So we said that igneous rock is, the fault is older. than the igneous intrusion A. What's our main topic, the intrusion or the fault here? If you had to put this question now into an answered sentence, what would you say? Fault H is older than igneous intrusion A, so our main topic again is the fault. So what's our reasoning now? The intrusion is younger than the rock layers. What is our main topic? The fault. So what are we talking about? The fault. So therefore, what's our principle? 3. The fault is younger than the layers that it breaks. This fault is not younger than the layers it breaks because it broke it. I'm sorry, this fault is younger than the layers that it broke because in order for those layers to be there, it had to break it. But it did not affect any of the other layers. So we're talking about the fault being younger than the breaks, excuse me. But if you were to put reasoning 2, then there wouldn't be a problem with that because they really both do explain it, correct? So they both give an explanation. So that was a little tricky one. All right, moving on. Number 4 says the surface at J. Where's the surface? Here or here? Let me do different colors. Is the surface the blue or the green? Blue. Surface means on the top portion. So the surface at J, is that a fault, a disaster, an unconformity, or an intrusion? What is that? What's a fault? What is a fault? A break. Is that a break? No. What is a intrusion? Okay. What's an unconformity? Wipes the rock out. Now, when rock layers lay, remember we looked at them laying how? Perfect, right? That's an undisturbance. What could happen to make that top layer look disturbed? Erosion, which is a unconformity. This jaggedy edge there says that something happened to brush some of that layer away. So all of it's not gone, but there's some of it gone because it doesn't look like a straight line like this. It doesn't look like a straight line like that. It's jagged, which means some pieces were removed. Pieces being removed would be considered what? An unconformity. Which principle would help us to answer this? The last one. An unconformity is an area where erosion has removed some of the rock layers. All right? Which is older, fault H or rock layer C? H is here. See that H? Okay, you're saying rock layer C is older, which means it came first. It came before because in order for it to be broken, it had to be there. Which, excuse me, which would be your explanation? What are we talking about? What is the question asking about? Is it just talking about layers? It's now thrown into the fault. So the reason it would be the fault is younger than the layers that it breaks. because this says that your C is older than the fault, therefore your fault must be younger than the layer that it breaks. Got it? Okay. And the reasoning is not something that you'll be tested on. The reasoning is there to help you explain why you chose that answer, to help you understand your answer and understand the layers. All right, now, lastly here, we must list the order of rocks in this diagram from oldest to youngest. Take a moment and see if you can do that. Now that you have your principles. And I believe you have a line down here. Put your oldest here. And go to your youngest. I may have labeled that, I'm not really sure. Okay, good. I am going to start labeling mine here, starting at the bottom, and now we'll be started at the bottom. Now we're here. At the bottom, there's no youngest. We don't do that. We don't see those layers. We don't see that. This is how we explain it. It's the law of superposition. All right, come on. What layer goes first, or the oldest? What's the oldest? E. Everyone agree? Okay. What would you say comes next? G. Okay, that's simple enough. We haven't gotten difficult yet. What would come next? L. C. All right, here's where we get a little tricky. Okay, now you say H, the break. I'm just putting this down here because you're saying it. Then M. What is H? The fault, okay. Then you say M. Then D. J. A. N. C should be, you think after C should be A? No, because we just discussed that in one of these where if M was affected by the intrusion A, because M is, this is M right here, pieces of M over here, that was affected. If M was there, it would have been broken as well. M wasn't there. So let's check and see if you're correct. Looks like you're correct. Give yourselves a round of applause for doing so well. All right. Flip the papers over to the back. We'll do some more practice. Flip it over to the back. Oh, let me go back to the front for a second. Your question at the bottom says, which law supports this? Law of superposition. All right? Flip it over to the back. Take a moment and see if you can work on the 2 at the top on your paper on the back. All right, for this diagram, what's the oldest? E, okay. What's next? B. Let me ask you this. Even though this is not labeled, what does this represent? Folding. That's not folding. Folding means that the rock layers would actually look like that. Unconformity. Folding would mean that you would have layers that actually look like that. And your layers do not look like that. Instead, the top of a layer looks a little jagged. So that would be an unconformity. All right, so you told me E, then C. Okay. E, then B, which is a intrusion. Then what? C, D, and A. If we label the unconformity, if this was an unconformity that was labeled, would this, what order would this have come? If this was Z, what would then be the order of the this rock layer? E, B, Z, then C, D, A. That means E and B are affected by the unconformity, so they had to be there, okay? This one here, that's just the way that stuff just, because remember it was molten lava, so it was a liquid. E, B, C, D, A. I added this Z on here after the fact. Okay? What about this one? Stop it! Stop! Let me ask you a question. What's A? An intrusion. A is not sedimentary rock because sedimentary rock lays as layers. That's not sedimentary rock. So what was first? C. C is the sedimentary rock. C is the sedimentary rock. Sedimentary rock are layers of rock that has been laid down almost perfectly. When you have something that looks like a flowing rock, that's igneous rock, which is a liquid that hardens. Okay? So what comes first? C. C is the rock layer, then A. Then you said A, then B. A is a intrusion. B is a intrusion as well. So you had two intrusions in this rock layer that broke through. You can see that A affects C because there's some C on this side, there's C on this side, and there's C even in there. Remember, it was a liquid. Okay? Always start from the bottom so then you'll be here. Okay? Trying to help you. Trying to help you. Drake's trying to help you. I don't know. In one way. I just wish he would deposit money in my account. All right. For this layer, notice again the sedimentary rock is layering in an undisturbed fashion. It looks like perfect. So what comes first? C. Is B affected by A? Yes. Therefore, had to be there. You can't have liquid just go above and turn into hardened rock just right above the surface. It would have flowed and layered out. Okay? So when this intrusion came about, if B wasn't there, it would have layered all the way across because it's a liquid. A liquid lays on the top of a surface and then it would have hardened. But it did not do that. Instead, it just broke through and flowed within that rock and then hardened there. So it had a molding to be able to harden around. B and D provided that molding. Okay? Any questions? Yes. It's just a liquid. It's just I can't explain why liquids do what they do. Remember, they're free flowing. No specific shape. Okay? That's your Beyonce, remember? Was Shakira the liquid? Oh yeah, Beyonce. Yes. That's right. All right. And then I think this is the second to last one, a little bit more difficult. So we're progressing in difficulty. God bless you. This is a G, in case you guys can't see it. All right, what comes first? Do you need a lifeline, or is that your final answer? Final answer. You don't have a lifeline. All right, G. Okay. How many of you say C came next? Okay. See if you can go further without me first. See how far you can go before I start being Vanna White. Excuse me, and uncovering the blocks. How many of you still watch? No, do it by yourself first. On your paper. How many of you still watch Wheel of Fortune? Oh, good. Okay. It's not a lost show. Take a moment and go ahead and see how far you can go before I uncover them. We'll get to that in a second. No, it's right. Remember that wavy line above represents a what? All right. Here's the lovely and beautiful Vanna White, or T-Dubs. Right here. That's me. I should get a round of applause for that. All right. So G, C, then you say A. You would be correct. Then yes. Oh. What? Is F broken? If F was broken, where else would you see it? On the other side of B. Remember, it breaks and it shifts. There's no other part of F over there. So therefore, remember, when a break happens, it shifts the rock. So you have the rock layers like this. Once you break it, some kind of drops down, which makes the layers now uneven, which gives it space for sedimentary rock to come in and fill that space. And that's what F did here. It filled the space after the break. Ooh, gotcha. For those of you that didn't do that, fix your mistake now on your paper and go further before I uncover the rest. All right, what next? Now you say F. Okay. Then what? What's this first? But let me just ask you this. What is this? Unconformity. If someone asks, is it liquid? It's not liquid because it's a jagged edge. It shows that there has been something that has happened there. Some erosion has occurred on that layer. All righty. You ready? You said H? Did E affect H? Now what? Stop for a second. Listen. Who says E is next? No, I. Who says I is next? Remember, E is the fault. Did E affect I? No, because there is no I on the right side. There's no I rock over here. So therefore, I didn't break. When the break E happened, the rock layer shifted where D right here dropped from there, providing a space for I, sedimentary rock I, to be layered, which means I is the youngest. Right? Any questions? All right, very good. We're going to save this one for later. You're going to actually work on that one on your own. And let's take out your sheet of paper, your blank sheet of paper, and we're going to take some quick notes on absolute dating. While you're getting your paper ready, someone raise your hand and explain to me what relative dating is. Not your cousins, your sisters, your brothers, uncles, and your aunts. Not being exactly, but close to, using words like what? Younger or older, which is what we've been doing. Now we're going to talk about absolute dating. You don't need to put the Roman numeral 3. Just put the word absolute dating. And this is going to be your title, which is your next set of notes that will go in your table of contents. This is on a separate sheet of paper. So now that we know what relative dating is, what would we say absolute dating is? Well, not actually know if youngest or older, because we're not, that's kind of close, but we're not using those words. Now we are using numbers. We're using exacts, no estimates. Now we're using the numbers to explain. So, absolute dating uses what we call radiometric dating to measure absolute age of an event or object using time. For example, years. Now we can say the Earth is this many years old, or the fossils in the Earth are this many years old. We're no longer saying this rock is older than another rock. We're now saying that this rock layer is 4 billion years old, or 2 billion years old, or 1 million years old. And just make sure you underline what I have underlined. What's radiometric dating? Well, I'm glad you asked. Before we discuss what radiometric dating is, we need to discuss index fossils. Now, index fossils are found in rock layers of only one geologic age, and they are used to establish the absolute age of that rock layer. They're not in multiple layers. Again, it tells you that they're only in one layer, which means the organism that fossil represented only existed during that time period. Does everyone understand that? Where's your index finger? Everyone lift your index finger. You use this finger to do what? Point. So that's how you can remember an index fossil. An index fossil, use your index finger to point to the fossil that's going to tell you the age. Okay? You only can point to it in one place. If it was in multiple places, you'd be pointing all over with a bunch of fingers. Because you only can point one place at a time, that's your index fossil that's going to tell you the time. An index fossil will not be located in any other layers. You will just find it in one index finger, one layer. You understand how I'm giving you the clues here? Okay. So between radiometric dating and index fossils, this is how scientists are able to explain or give an absolute age of layers. Radiometric dating. It's going to use the rate of decay for a radioactive element. We talked about elements in chemistry. Scientists know how long it takes different radioactive elements to decay. So they know the lifespan of decay for a certain element. And elements are located within fossils because those were living organisms. And we all know that every living thing is made up of carbon, hydrogen, oxygen, and nitrogen. There is some decay within carbon. Carbon decays at a certain rate. Scientists know that rate. So if a scientist was able to dig up a fossil, check how much carbon was left in that fossil. Knowing the lifespan and how fast it decays, they can go backwards to determine how old that fossil is. And we're going to do some examples to help you understand, because I know you're writing and you're not taking in anything that I'm saying right now. There's not a lot of writing for these notes, so this is just about almost all you're going to be doing. So we're going to have some examples that'll help you explain it. Don't write this yet, because I want to explain it. Everyone look up at me, stop writing. What I mentioned just a moment ago in radiometric dating. Remember, radiometric dating, like I said, is used when we look at fossils. Fossils are evidence of not just dinosaurs, but living things, the evidence of living things. When we talked about chemistry, we took notes and understood that all living things contain these specific elements, being carbon, hydrogen, oxygen, and nitrogen. Carbon is a radioactive element, which means that it decays. What does decay mean? It disappears over time. It breaks down over time. Scientists know the lifespan of carbon. They know how long it takes for carbon to decay. Carbon or any other radiometric element decays in half-lives, which means after a certain amount of time, half of the life is disappeared. So they know that, let's say for instance you have a whole amount of carbon. Let's say it takes carbon 1 billion years to decay, half-life. So in 1 billion years, you will no longer have 100% carbon. You will now have 50%. In another billion years, you will now have half of what's there, 25%. In another billion years, you will have 12.5%. If a scientist dug up a fossil and there was only 12.5% of carbon, how old would that fossil be? How many? 3 billion years old. We've only went by 3 billion years to get to 12.5. Do you understand how that works? Okay, we're going to do some examples. So radioactive occurs at a steady rate. Scientists use the relative amount of stable and unstable elements. So what I want you to write is, don't write this exactly. I'm going to tell you exactly what to write. Radioactive decay occurs at a steady rate. Do write that part. Scientists use the amount left, in parentheses, put stable, and the amount decayed, put in parentheses, unstable, to determine the age. I'll say it one more time because I don't want you to write this because this doesn't make sense to you. It's better written the way that I explained it. Radioactive decay occurs at a steady rate. Scientists use the amount present, in parentheses put stable, and the amount decayed, in parentheses put unstable, to determine the age, the absolute age. And under that, put measured in half-lives. JD. To determine the absolute age. So like we just explained, scientists are going to see what's left, what element is left. They then look up and see what's the decay rate in half-life for that element. So again, let's say if they look up carbon, they say, oh, we have some carbon left. How much carbon do we have left? What is carbon's half-life? Carbon's half-life, let's say it's 2 billion years. Okay, so they take how much they have left versus the half-life, and see, they go back to see how many half-lives have occurred before they get back to 100%, and that's how they determine how old that fossil is. If that fossil is that age, then it is safe to say that that rock layer is that age, and that's how we date the Earth. Okay? Let's move on. So, for instance, let's say the Hershey bar that's within this rock, let's say that this is the rock layer, this block out here that I'm lining in blue. Within the rock layer, you have a fossil, which I'm outlining in red. Within the fossil, you have an element, and the element is the chocolate, okay? Let's say scientists saw this element and they determined that this element has a half-life of 15 seconds. Okay, now this is actually going back in time, and we're looking within the rock layer and viewing what's happening in the past. No one can see that. Actually, what they see is what's left, but we're looking at it as if it has all of the elements there, okay? This organism just died. The fossil is not really there, it's just the organism. So, in 15 seconds, what should happen? Huh? Half should decay, which means half of that chocolate element should disappear. So everyone count to 15. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. No, we're only counting to 15. 15 is the span, is the half-life span. So after 15 seconds, we only have half of that element. If scientists were to dig up this fossil, see this fossil, take a look at the element that is present, and saw that they only had this much, 50% of the element, they would say that that fossil is how old? 15 seconds. And another 15 seconds, what should happen? Okay, so let's then say that 15 seconds has occurred. If scientists dug up this fossil, they would then say, how old is this fossil? 30 seconds old. Let's say another 15 seconds has occurred. What should happen? It wouldn't be gone. Half of it would go away. Scientists dug this up. How old would they say? 45 seconds. Again, another 15 seconds has occurred. What should happen? Now, how old is that? A minute. So let's say scientists dug this up and this is what they saw. They would then have to backtrack, okay, in 15 seconds, do I have all of it? And another 15 seconds, do I have all of it? And another 15 seconds, would I have all 100%? How far back do I have to go to get 100% of that element? When they go back that far, that's how they determine how old it is. And we say that this piece of fossil that's there is, it's not, we know that this is 1 minute old, which therefore this rock layer would be a minute old. I mean, everything still occurs in 50%. 50% of what's there. It's 50% of the life that's there. All right. So, has a half-life, okay, this green element has a half-life of 10 seconds. So after 10 seconds, how much of this green element should go? Half of it, okay? So in 10 seconds, let's say 10 seconds has occurred. This is what we have now. How old is the fossil in this? 10 seconds. How old is the rock layer where this fossil occurs? 10 seconds. This element within this fossil still has a half-life of 10 seconds. After 10 seconds, what should happen? Half of what's there should disappear, which then we're with this. How old is this rock layer? 20 seconds. You understand so far? Okay, I'll do one more example. This is where we get a little bit difficult. The element, the red element, has a half-life of 5 seconds, and its stable state is 10 seconds. How old is this layer of rock? It says 15 seconds. I'm going to leave this for your thought because I want to come back to this at a later time to build on it. But what I do want you to understand is we go back one more, you do understand how scientists go ahead and use what it is that they have. So if they look at this, let me do this actually. If they look at this element here, they would say, okay, after 5 seconds, because it has a half-life of 5 seconds. After 5 seconds, I should have half back, because they're going backwards. So in 5 seconds, I have half of mine's back. So far, this element is how old? I'm going back 5 seconds. So I know that 5 seconds has occurred. Because what I had was this. I'm trying to see how old this is, but in order for me to see how old this is, I got to go back in time to see how much I'm going to have all of mine stable. Stable is 10. I mean, I need 10 of these total. Okay? So in 5 seconds, I go back, excuse me, do I have 10, which means that's 100% of my element. Do I have 10? No. So far, this element that's there is how old? 5 seconds. Okay? That's my half-life. In 5 seconds, I need to gain another half of what I have. See, I had half of this one here. In 5 seconds, I go back, I gain half, which means I'll have half a circle and 2 more. So how old is it now? 10 seconds. I've lapsed 5 2 times. That's 10 seconds. Do I have 10 pieces of red dots? No. Okay? So I go another 5 seconds, which gives me this. How many seconds have I went back? 5, 10, 15 seconds in order for me to get stable. So it took how many seconds to get stable? 15, which means it will take how many seconds to get back to what was only there? 15. So therefore, this is how old? 15 seconds. Got that? Okay. Very, very good. You have to unless you didn't see it. So explain to me then how absolute dating works. Write that down in your own words. Write this down. Explain how absolute dating works. And while you're doing that, I'm going to give you a piece of the fossil. All right, someone give me in your own words how absolute dating works. How does absolute dating work? You should be able to give me an explanation because we just did it and we just talked about it. Go ahead, Francis, let me know.
Absolute dating is when scientists...
Wait. I'm sorry, let me start writing. Hold on one second. Okay, he says absolute dating. Go ahead. Keep going. When scientists use the, do we have to just use the carbon? I'm going to use this word. when scientists use the existing what? The existing available what? Element. In what type of fossil? What is the fossil that we have that helps us determine absolute dating? Index fossil. Does this truly explain it? I don't know. Check the spelling on this. I'm sleepy. Absolute, I think that's right. Available. Yeah, that's right. All right. Absolute dating is when scientists use the existing available element in an index fossil. Should we put existing available? What should that mean? Why is it available? Because it's not what?
Non-decayed.
Non-decayed. So you can put existing available, but in parentheses, put non-decayed element in a fossil using, what do we use? How are we using to determine, what are we using to determine the age? How is it measured?
Like half-life.
Half-life. All right.